Hello and welcome to Empowered Learning. This particular video will be about solving radical equations or nth root equations. And so we start off by defining what a radical equation or an nth root equation actually is. So we see here that an equation that has more than one or more expressions where the variable of the equation appears in the radicand is called a radical equation. Okay? So here we would just put radical equation. The principle of power states that for any positive integer n, that if we have one expression equaling another, then that also means that we can take that expression and raise it to the n power, and that will be the same thing as the other expression b raised to the n power. Now, the reason why I'm quoting this is that we need to take into the fact that whenever we are taking radical equations and trying to solve them, one of the ways that we could solve it is by changing the radical expression on either side of the equal sign into an expression where we have a fractional exponent. Okay, in some cases we can take both sides by raising both sides to the n in the power of n to be able to essentially get rid of the radical signs. And so we'll see some examples of that. The other point that I want to bring up whenever we start to solve these type of equations here is that when we solve a radical equation, it's best to isolate an expression that has a radical in the equation all by itself on one side of the equation and everything else on the other. And so the purpose of that is, let's say we have square root of something in the equation. If we get that term with the square root by itself on one side, we can square both sides or raise both sides to the power of 2. And so by doing that, that essentially makes the square root sign go away on that one side where you isolate the radical expression. And of course, if you have more than one radical expression like that, you would do it in succession. Let's say manipulate your equation to get one side of it just with that radical expression, and then raise it to the power of n to get rid of that. And then if you have another one, remanipulate to get the other expression on one side of the equation and then raise it to the n power again. Okay, so the last thing that I want to comment on is that whenever we're solving equations, remember that we're solving graphical problems without actually having a graph. Okay, so it's always a good idea to check radical equations for the solutions that the process gives you, just to make sure that they are correct. Just like with rational equations, there's sometimes the process actually gives you answers that actually don't work. Okay, and so it's good to check. If you are familiar with the graphs of how some of these functions look in the equations that you're asked to solve, then that'll pretty much give you an idea of if you get what's called an extraneous solution or not. Throughout this particular video, for some of the equations, I will be giving you the graphical representation of what the equation is actually asking you to do, so that you can sort of get a feel for that. It's not necessary for you to know how to draw these graphs. I'm just wanting to do this to give you some perspective on what your actual equations are trying to communicate to you, and what type of information it's trying to get you to answer about the actual graphs of these functions in the first place. Okay. All right, so with that, we'll go ahead and get started. So we'll take some easy ones here to get started with, and then we'll move on. So let's go to example B first. You see, for example B, we have the cube root of 5x minus 2, and that is equal to a negative 3. And so we notice here, to get rid of the cube root sign, we're going to have to raise the left side to a power of 3. Well, what we do to one side, we have to do to the other. So that means we'll raise -3 to the power of 3 as well. And so with that, that essentially makes the cube root sign go away whenever we raise both sides to the power of 3. So we just have 5x minus 2. And on the right side, we know that -3 cubed is just -3 multiplied times itself 3 times, which gives us a -27. So from that point, we have a nice linear equation there, and we just solve it for x. So we add to the both sides. We get 5x is equal to -25, and then divide both sides by 5, and we get x is equal to -5. Okay. Now, to check this, we just plug in -5 back into our original equation, which was here, and we see that whenever we do that, we end up having -3 equals -3. So this is actually a valid solution. Okay. So with that, let's go ahead and move on to A. So with A, sort of the same thing. We want to get rid of the square root sign, so we need to raise both sides to the power of 2. And that will essentially just leave us with 7 minus x equals 4. And then, of course, from that, we can subtract 7 from both sides. That cancels to 0. And here we could divide both sides by a -1. Negative divided by negative is a positive. Negative divided by negative is a positive. Okay. And so, of course, if we went ahead and substituted 3 back into the equation here, then we would see that we have square root of 7 minus 3, which is square root of 4. And square root of 4, the principal root of that is 2. Okay. So we see that 3 is actually a valid solution to this particular equation. Now, one thing I do want to call to your attention is what this actual equation was originally saying. So I'm going to pause for a second to get rid of all of this and kind of draw the graph of what this would look like so that you can get an idea of why 3 would actually be the answer. Okay. Okay, so I've erased the work that we've previously done, and I've drawn a graph of what the function square root of 7 minus x would look like. So that's this function that's going like this. So what this actual equation is asking is give me the x value for the function square root of 7 minus x, which looks like this, when your y coordinate on the point of that graph is 2. So put another way, here's the point. If your y coordinate is 2, what is your corresponding x coordinate? That's what this equation is actually asking. And so as you see here, when this function has a y coordinate of 2, from what we saw earlier, the x coordinate, the corresponding x coordinate is 3. Okay. And of course, we went in and we checked that and we saw that that was indeed the answer. Okay. Now, what we're doing whenever we solve these radical equations is we're basically doing a process of figuring out the same information as what I've drawn here, but without me actually having to draw a graph to do it. Okay. Now, I'm only showing this so that you can have perspective here and understand that because of the way that square root of 7 minus x looks, we would only have one answer. Okay. If we would have did this process and came up with 2 answers, we would have known just by how the graph of square root of 7 minus x looks that one of those answers wouldn't work. Okay. And so that's part of what I mean by having perspective on knowing what answers kind of work and which ones don't, even if the process spits out like more than one answer. And even if it does spits out one answer, knowing what the graphs of some of these functions look like will let you know if that one answer is actually one that works or not as well. Okay. Now, in saying that, let's go ahead and move on to example C. And you'll see here that we have square root of x minus 10 equals -5. Now, the answer to this one is no solution, and I'm giving it to you by the null set there. And so there's two ways we can think about this. So for the first way, we know that if we plugged in some real number value for x, okay, the first thing that we know is whatever it is that we come up with, whenever we take that and do the square root of it, we know that we're talking about the principal root, which is always a result that is non-negative, okay? So in short, if we take the square root of anything and we're taking the principal root of it, we should always come up with an answer that's not negative. This particular question is asking us to essentially plug in an x value here. Let me get rid of that. It's actually telling us to plug in an x value and take the square root of whatever the radicand is to get a negative answer, okay? And of course, we know that for what we're doing, that's just not possible. As I explained earlier in the series of videos for radical expressions, we talked about this whole thing of what the graph of y equals square root of x looks like and how we can only consider non-negative answers for y in this case, okay? Now, similarly here, the graph of square root of x minus 10 sort of looks like this, okay? And so if you notice here that I'm not going to be able to have a corresponding y coordinate on the graph of this particular function that's going to be negative. In other words, I'm not going to have points down here on this graph. So here we say that this is no solution because on the graph of square root of x minus 10, there is no point that is below the x-axis, okay? So that's the other way to think about it. So anytime you're asked for square root, fourth root, sixth root, eighth root, 10th root of whatever it is, if it ends up equaling a negative number, you know that there is no solution to that if we are taking the principal root, okay? Now, for example D, this is a fairly simple example here. Notice that t raised to the 1/5 is also the same as the fifth root of t, okay? In either case, whether you write it in nth root form or in fractional exponent form, we could raise both sides to the power of 5 to essentially find out what t is. Of course, if we do t to the 1/5, all that raised to the 5, that's the same as t to the 1, because 1/5 times 5 is 5 over 5, which is 1. 2 raised to the 5th power is 32, and anything raised to the power of 1 is just itself, okay? So we have that answer there. Moving on to example E now, we have the situation where what we want to do is get this square root of x plus 7 by itself, everything else on the other side, and then since it's square root, we want to raise both sides to the power of 2 to get rid of the square root sign and then try to solve for x, okay? So to do that, we will subtract both sides by 5. And if we do that, of course, that goes to 0. We have square root of x plus 7 on the left and x minus 5 on the right. And of course, here we will square both sides. And on the left side, that will just leave us with x plus 7. On the right side, if we were to FOIL this out, this is the same as saying x minus 5 times x minus 5. So if we multiply that out, we would get x squared minus 5x minus 5x and plus 25, okay? And of course, negative 5x and negative 5x combine to be a negative 10x. So from here, we would just solve this by subtracting x to both sides, subtracting 7 to both sides, because we realize now this is a quadratic equation. All of this cancels to 0, and we have x squared is equal to minus 11x plus 18. And so from here, we have to remember what we did back when we were dealing with quadratics and factoring, that here we have minus plus, so that means we're going to factor this. It's going to be x minus, x minus. The factors of 18 that add up to be negative 11 are a negative 9 and a negative 2. So we'll just place that there. And so we know that that either means that x minus 2 is equal to 0 or x minus 9 is equal to 0, which in turn, here if we add 2 to both sides, that just means that x is equal to 2, or that x is equal to 9 if we add 9 on both sides. So 2 or 9 would be the solution there. Okay. Now, of course, if we go and check our answers here, we'll have 5, and I'm just going to use x equals 2 as the first one. So 5 plus 7. Oops, sorry. That should be 5 plus square root of 2 plus 7. And that equals 2. Of course, that would be square root of 9. Principal root of 9 is 3. And this should be, kind of messed that up here, so let's fix that. This should be a 2. And so you see here that 8 does not equal 2. So we see that the answer 2 is what we call an extraneous solution. Okay, so we know that the 2 would not work in this case. Notice how the process gave us 2 as an answer, but when we checked it, we see that 2 was not it. And again, I'll draw the graph of this later to kind of show you why it ends up being that way. Okay. All right, so we know that 2 is not going to be a viable answer. So let's go ahead and check this again with 9 and see if that works. Now, so I'm just going to erase all this and kind of see if we can work this out now. Okay. So now if we plug in 9, here we know that that's going to be 5 plus square root of 16. Square root of 16 is 4. And of course, let's get rid of this, get rid of that. Let's get rid of all this, really. Have 9, and of course 9 is equal to 9. Okay, so we see that x equals 9 is the actual solution. Okay, and it's the only solution to this. All right, so again, I'm going to pause and draw the graph of what this equation would look like and show you why we only have one answer to it. Okay, so I've erased the work for the last problem, example E here, and now I've drawn the graph of what this equation is actually trying to communicate. So as you see here, we could treat the left side as a function, 5 plus square root of x plus 7. And of course, that function looks like this one here, much like the square root of x type function looks. And then over here on the right side, we just have x. And if we look at that as y equals x, then that looks like this straight line we have here. And so essentially what this equation is asking for is, when does the function 5 plus square root of x plus 7 and the function y equals x, when do they intersect? And if you notice, the intersection point is right there, okay? And so you see that it actually intersects when x is equal to 9, which was one of the actual solutions we had. The other solution, which was x equals 2, if you notice, x equals 2 would be about here. If you notice that that doesn't work according to how the graph of this looks. Now, the reason why x equals 2 would look as a possible solution it would look that way only if you misinterpreted what the principal root of square root of x plus 7 would look like. So I'm going to write this back again and use 2. And so let's say here we decided to take square root of 9 and say, all right, well, we can interpret this as being a negative 3. So if we did that, it would be like this, and then you would have a 2. But again, we know that we can't take the square root of anything, and for its principal root, which is in accordance to how the graph looks, assume that it's going to be a negative answer. And the reason for that is because if we went that route, we can't just say that square root of 9 is a negative 3. We would have to say that it's plus or negative 3. So we would have to actually do it this way, okay? Which means that either 8 or 2 would be an answer. And thus, we would have a situation where we have a graph that sort of looks like this again, okay? And we know from what we talked about earlier in the radical expression videos that that's not a function, and of course, nothing ties together at that point, okay? So it's not necessary for you to know how to draw these graphs, depending upon what course you're in, but it is necessary for you to understand what this equation is actually asking for and why we actually have to go check our solutions, okay? If you have an inclination of what the graphs of these functions will look like, then sometimes you can sort of figure out which one or which ones are the extraneous solutions without actually having to go through the answer checking process, okay? All right, so we're going to go ahead and get rid of this and then move on to example F. All right, so we have an abbreviated version of the work we did for example E back up, and now we are going to work on example F. So again, sort of the same thing. We have square root of 5x plus 1 all on one side of the equation. So we're just going to square both sides here. On the left side, we just end up with 5x plus 1. Oops, excuse me. Let's get rid of that. Do a plus. And then here we know that x minus 1 squared is just x minus 1 times x minus 1. And if we multiply all that out, we end up getting x squared minus 2x plus 1. So you could actually take x minus 1 here and FOIL it out if you're not familiar with how to look at this the shorthand way. All right, so at this point, we realize we have a quadratic equation because our highest exponent is a 2 on any variable. So we need to get everything to one side. So we subtract 5x and subtract 1 from both sides. Our left side comes out to be 0, and our right side will just be x squared minus 7x, where this 1 minus 1 is 0. So here we factor out common factor of x. And so now that means that either x is equal to 0 or x minus 7 is equal to 0. And if we add 7 to both sides here, we see that x is 7. So here, x is either equal to 0 or x is equal to 7. Now we need to check to make sure that both of these solutions work. So I'll go ahead and do that for us right quick. I'm going to go ahead and get rid of all this stuff for E and then check each solution on this side to make sure that it works. Okay, so now that we have side E cleared up, we're going to go ahead and plug in x equals 0 and x equals 7 into these to see if these are valid solutions or not. So we'll start off with x equals 0. So we'll come here and say square root of 5 times 0 plus 1 equals 0 minus 1. And of course, 5 times 0 is just 0. And 0 plus 1 is 1. So we have this situation here. The principal root of square root of 1 is, the principal root of 1 is 1. So now we have 1, which is not equal to -1. So that means that x equals 0 is what we call an extraneous solution. So now we need to check and see if 7 works. And so I'll go ahead and get rid of this right quick and try 7. So now let's do x equals 7. We plug in 7 into here, have that equal 7 minus 1. Of course, 5 times 7 is 35. 7 times 1 is 6. 35 plus 1 is 36, and then square root of 36, the principal root of that is 6. So that is our valid solution. Well, we see that both sides are equal, so therefore x equals 7 is our actual valid solution. And so again, I could draw the graphs of square root of 5x plus 1 and the graph of y equals x minus 1 and show you that the only place where those two graphs intersect would be at x equals 7. Okay. All right, so we'll go ahead and move on to some different examples now. So moving on to example G here, we see that we have two expressions that have radicals in them. So we're going to end up having to square both sides of the equation twice. Okay, so we're going to start off by getting this particular expression by itself and putting everything else on the other side, squaring both sides, and then reworking the problem and getting all terms, well, getting the term with the radical in it then by itself, and then squaring both sides again. So it's going to be a little long of a process, but if we take it one step at a time, we should be fine. All right, so first thing we need to do is add square root of x to both sides, okay? And so if we do that, we'll have square root of 2x plus 1 on the left, and we will have 1 plus square root of x on the right. And now we have a situation where we have radical expression isolated by itself on one side of the equation. So we're going to square both sides, okay? So square root of 2x plus 1 is just 2x plus 1. And on the left side, we are going to multiply this out. And if we do that, we'll have 1 plus 2 times square root of x plus square root of x squared, which is just x. Okay. And again, we're not doing absolute value of x here because for our original equation, we noticed that in order for us to have real number solutions, since x is under the radical here, x would have to be greater than or equal to 0. Okay. So similarly, we could look here, and we know that this has to be non-negative as well. So we could say 2x plus 1 is greater than or equal to 0. And if we solve that, we would see that x would have to be greater than or equal to a -1/2. So looking at x being greater than or equal to a -1/2 and x is greater than or equal to 0, x greater than or equal to 0 trumps that. So because of which we can assume that all the x values that we can plug in here are going to be something that's 0 or higher. So no absolute value signs needed. So that's the purpose for that. All right, so once all that's done, we see that this is the only expression with the radical in it. So we're going to move everything over to the left side and just keep 2 times square root of x over on the right, and then square both sides again. Okay, so here we will subtract 1 from both sides and subtract x from both sides. And if we do that, then of course, get 0, 0, and 2x minus 1x is just x. And that's 0, and we just have 2 times square root of x there. And of course, again, we will square both sides. So on the left side, we just get x squared. On the right side, we get 2 squared times square root of x squared. And of course, that would just be 4 times x. Again, we're not doing absolute value of x here because we know x has to be greater than or equal to 0. So from here, we know that this is a quadratic equation. Put everything on one side. So we have to subtract 4x from both sides. Factor out common factor of x. So that means that x is either equal to 0 or x. Oops. Let's try to get that equal sign looking a little better here. So we have x is equal to 0 or x minus 4 is equal to 0. Let's get that 4 looking a little better. So if we come up here now, so that either means that x is equal to 0 or x is equal to 4 if we add 4 to both sides there. Now, again, we'll need to check our original solution here. Well, we need to check the solutions in our original equation to make sure that both of these solutions work. Okay, so we're going to keep in mind here that x can either be 0 or 4. I'm going to erase all of this and then start with the checking the answer process. All right, so we're going to go ahead and start with x equals 0, plug this in, and see if we get a valid solution. So we plugged in 0 everywhere we can. We know that 2 times 0 is 0. 0 plus 1 is 1. Square root of 0 is 0. Square root of 1 is 1. And so this looks to check out. So x equals 0 is a valid solution. Let's go ahead and do the same thing with x equals 4. So let's go ahead and plug in 4 wherever we can. And we know that 2 times 4 is 8. And 8 plus 1 is 9. So we just have that. Square root of 9, the principal root of that is 3. Square root of 4, the principal root of that is 2. And of course, 3 minus 2 is 1. So it turns out that both of these solutions here are actually valid solutions. So that means the graph of whatever this function is on the left and this function is on the right would actually intersect at 2 positions or at 2 locations, and that would be when x is equal to 0 as well as when x is equal to 4. Okay. Now, just to address this, if you're wondering what is over here, this is example C if we would have worked it out the long way. And so I haven't talked much about absolute value equations in some of the videos that I've done. So if you're interested in that, of course, you could please check out the absolute value equations video so that you can sort of see what's going on there. But essentially, if we did this by using what we know about absolute value equations here, then you'll see that this first solution, if we plug in, was it x equals 35, x equals 35 will end up being our answer here if we did it this way. But of course, if we tried to plug it in, we would see that it wouldn't work. Okay, so my point here, and I'll go back to example C so that you could look at that. That was this answer here. I was trying to show you why this actually had no solution to it. If we could solve for a solution, that solution would look like x is equal to 35. But you see here that when we go ahead and work it out, we'll see that 35 would work for when y is equal to 5, not y is equal to -5. Okay, so this was just an addition I added on for example C that I couldn't fit on that page, that sort of explained from an algebraic perspective why we had no solution there. Okay. All right, so for example H, I'll just pause for a second here. I'm not going to go through this one extensively because there is a lot going on with it. But at the end of the day, the main thing to understand is that the process is pretty much the same. Okay, so we go through, we see they end up having a quadratic equation, factor it, we check our answers here, and we check when m is equal to 2, m is equal to 42, and we see that 42 does not work, but that 2 does work to be a valid solution. Okay. All right, so we'll go ahead and move on here. And so this particular page is talking about example H, and that would be this example here. What I've done is taken the liberty of drawing the graph of this function and this function superimposed on the graph so that you can see that the graphs only cross where m is equal to 2. So and that's pretty much what I'm trying to explain here. So if you see, and I'll reduce this so that you could see it all. If you see here, the blue graph is the graph of square root of m plus 7 minus 2, and the dark black graph is the graph of square root of 2m minus 3. And you can see where they both intersect. They intersect when x is equal to 2 there. Okay, so I'm not quite sure if we know where this is. It may be up here or down there, but of course we know that when x is equal to 2, that's where they both intersect at, and that's the point that I want to make. And so if you know how both of these graphs look, you know that it will only intersect at one point anyway, so you'll already know that one of the solutions is not correct. And of course, just based off how these graphs look, if we go back here, we'll see that m being 42 is preposterous because that's like way out here somewhere. Okay, and of course these functions long, are pretty much spreading apart from one another way beyond that point. Okay, all right, so let's go back here and look at this next example. And so if we're asked to find the zeros of this particular function, and this should be an x right there. So the function g of x is equal to x plus square root of x minus 20. Of course, here this is the same as saying take x plus square root of x minus 20 and set it equal to 0. We're trying to find the zeros of it, the locations of where that function crosses the x-axis. Now, in some of my previous videos, we've gone through the process of how we actually solve these. So these equations, they're not quadratic, but we can solve them quadratically by using the substitution method. And so that's what I'm referring to here. We see that our issue is square root of x. That's the one thing that messes up this particular equation being quadratic in the first place. So we allow u, another variable, to be square root of x. And so from that, we know that if we square both sides, assuming that x is greater than or equal to 0, then u squared would be equal to x. So if we do that, we can replace square root of x with u and replace x with u squared. And we would eventually end up with this quadratic equation. So from that point, we gain simplicity by being able to solve the quadratic equation in terms of u, but the thing that we have to pay for on the back end for that is that once we get an answer for u, we have to substitute in what u was in terms of x, which is square root of x. Okay, so if we come in and we factor the expression on the left side of this equation here, it factors to u plus 5 times u minus 4. And so from there, that means that u plus 5 is equal to 0 or u minus 4 is equal to 0, which means that u has to either be equal to -5 or u has to be equal to 4. If we substitute back square root of x in for u, we see that for the first equation, we have square root of x is equal to -5, which we know is no solution because we know the principal root of any value of x that we plug in has to be a non-negative number, okay? For the second one, we see that square root of x equals 4, so if we square both sides there, of course, assuming that x is greater than or equal to 0, left side is x, right side 4 squared is 16, okay? So here we know that there's only going to be one solution to this particular problem, which is 16. And of course, we could always go back and check our solutions to see that it is indeed the answer. So I'll go ahead and do that now. So we have 16 plus square root of 16 minus 20, and we want to see if that equals 0. So square root of 16 is 4, 16 plus 4 is 20, and of course 20 minus 20 is 0. So that checks out. Okay. And so now what we're going to do is scroll on to the next page and show you how we could interpret this graphically. Okay. So here, what I've done, and I'll just shrink this so that we can see it again, to graphically see what the solution of this equation would look like, we could either graph this equation directly, or we could rearrange the equation to look like this. And this is sort of the approach I've taken here, to make it look like this, because it's easy, relatively easy for me to draw the square root of x graph and to draw the graph of the line 20 minus x. So we see the line 20 minus x is there. We see square root of x looks like this dark line here, dark dotted line rather. And if you can see, both of these graphs intersect when x is equal to 16 right here. Okay? And so again, want you to remember that whenever you're solving equations, that you're actually solving figuring out a graphical question without actually having the graph in front of you. Okay, really want to reiterate that and make that known. Okay, and so with that, this should conclude our discussion on solving radical equations.